In the years immediately following the Second World War, American aerospace research was largely confined to the atmosphere. The National Advisory Committee for Aeronautics, or NACA, focused heavily on atmospheric flight tests, distributing efforts across military and civilian branches. That strictly atmospheric focus abruptly shattered in late 1957. The Soviet Union successfully launched Sputnik, placing the first artificial satellite into orbit. It created an immediate technological vacuum for the United States, exposing a sudden and critical vulnerability in the Cold War. President Dwight D. Eisenhower responded by signing the National Aeronautics and Space Act. The directive was clear: consolidate the fragmented military and civilian space efforts into a single, aggressively funded civilian agency. On October 1, 1958, NASA officially opened for business. Its mandate demanded an immediate pivot toward reaching the vacuum of space. Almost overnight, the new organization absorbed thousands of NACA employees, major research facilities, and sprawling military rocketry operations, binding them together under one civilian roof. NASA was built as a centralized defense mechanism to win a geopolitical technology race, prioritizing strategic dominance over scientific curiosity in its earliest years. Reaching that orbital objective required intense foundational work. Before digital processing, calculating precise mathematical trajectories for spaceflight relied entirely on the labor of female human computers doing calculations by hand. Alongside the math came the biological testing. Engineers had to prove a living organism could survive the kinetic forces of launch and the disorienting effects of microgravity, relying on early animal flights to gather vital physiological data. Between 1964 and 1966, NASA launched Project Gemini. Over the course of 10 crewed missions, the agency tested the physical endurance of its astronauts and the capabilities of its orbital hardware. Gemini served as a critical proving ground. Before attempting a moon transit, crews had to rendezvous in orbit and execute complex spacewalks. Solving these problems in low Earth orbit provided the raw data required to turn theoretical deep space travel into a set of actionable, repeatable procedures. A decade of iterative engineering culminated in the colossal mechanical scale of Project Apollo. Escaping Earth's gravity well required a vehicle of staggering complexity. The Saturn V utilized a multi-stage design, systematically shedding mass as it accelerated to reach the velocity necessary for a lunar trajectory. Between 1969 and 1972, this architecture successfully delivered crews to the lunar surface, securing the geopolitical victory the agency was built to achieve. Having met its founding directive, the institution faced a sudden crisis of purpose. The race was over, and the enormous budget that sustained Apollo was drastically reduced. The agency pivoted. Instead of episodic sprints to the moon, NASA focused on securing permanent, routine access to low Earth orbit by developing a reusable space shuttle. This new cargo capacity allowed for an aggressive expansion into deep space science. Shuttles could deploy massive, unimpeded observatories like Hubble, positioned perfectly above the distortion of Earth's atmosphere. Over the following decades, the organization transitioned. It moved away from operating as a single-minded competitive racing team, expanding into a broad, multidisciplinary engine for scientific discovery. As shuttle flights became increasingly frequent and international cooperation expanded with the construction of the International Space Station, a sense of routine began to settle over orbital operations. The true spaceflight is never a routine operation. Re-entry requires a vehicle to survive intense kinetic violence and extreme thermal plasma as it plunges back into the atmosphere at orbital velocities. Pushing these physical boundaries carries a profound human cost. The loss of the Apollo 1, Challenger, and Columbia crews serves as a permanent reminder of the inherent dangers of aerospace engineering. Each tragedy forced the agency into rigorous periods of institutional reflection. Returning to flight required extensive mishap investigations, meticulous hardware redesigns, and sweeping cultural overhauls. These periods of loss definitively proved that exploration on this scale can never be treated as commonplace. It demands eternal vigilance and the acceptance of immense sacrifice. Today, NASA maintains a multifaceted approach. It continues to push the limits of Earth-bound aeronautics, testing quiet supersonic flight technology with vehicles like the X-59. Simultaneously, its deep space footprint has expanded. Intricate robotic rovers now traverse the harsh, ancient terrain of Mars, analyzing geological samples in real time. These robotic scouts map the environmental conditions and technical requirements necessary to sustain human life far beyond Earth's orbit. That human element is now the focus of the Artemis program. With crew members selected and a new heavy lift architecture in place, the agency is preparing for a crewed return to the lunar surface in 2027. The objective this time is to establish a sustainable, long-term human outpost on the Moon. It serves as the ultimate staging ground and technical stepping stone for an eventual crewed mission to Mars. In the 67 years since its founding, the organization has evolved drastically. It began as a frantic, reactive defense against a geopolitical rival. Today, it stands as an enduring institution dedicated to leading humanity into the unknown. For centuries, the distant outer planets were completely unreachable, merely static points of light suspended in an infinite void. Deep space presents a biological hard limit. The lethal combination of cosmic radiation, decades of travel time, and the massive logistics of life support makes human spaceflight to these distances currently impossible. To touch these worlds, NASA pivoted toward building mechanical proxies capable of enduring the conditions that would destroy a human body. Mastering the solar system is primarily an engineering and robotics challenge, rather than a test of human physical endurance. NASA met this challenge through specialized programs like Discovery and New Frontiers, which exist to fund and engineer bespoke robotic probes for specific mission goals. These instruments are built with extreme precision. Every component must survive violent launch vibrations and the absolute zero of deep space vacuum. Controlling these machines requires a massive communications backbone. The Deep Space Network uses a global array of satellite dishes to bridge the planetary gap, transmitting commands and receiving data from billions of miles away. These machines serve as humanity's physical extensions, acting as our eyes, ears, and hands in the dark. Mars serves as our immediate planetary neighbor and the primary testing ground for extraterrestrial contact. We moved quickly from early flybys to static landers. In 1976, the Viking probes anchored to the soil, providing the first direct observations of the desolate Martian surface. Modern exploration is defined by movement. We transition to deploying massive rovers, mobile laboratories like Curiosity that can traverse craters and navigate complex terrain. Curiosity discovered the chemical ingredients necessary for life, while simultaneously mapping surface radiation levels to prepare for future human arrivals. The Perseverance mission escalated this capability even further, successfully deploying the Ingenuity helicopter to achieve powered flight in the thin Martian atmosphere. This robotic armada transformed Mars from a distant observational target into a continuously monitored physical laboratory. The journey continued outward, crossing the asteroid belt to confront the massive scale of gas giants. Pioneer and Voyager 2 were the pathfinders of this era, built specifically for these pioneering flybys into the outer solar system. Their trajectories intersected with Jupiter, Saturn, Uranus, and Neptune, where they captured unprecedented data about the outer neighborhood. To reach these speeds, the probes utilized gravitational assists, slingshotting around the massive gravity wells of Jupiter and Saturn to accelerate toward their next targets. These early flybys provided our first close-up maps, but their fleeting nature demonstrated the need for probes that could enter orbit and stay. We followed the flybys with heavy orbiters, missions designed to lock into planetary orbits for long-term study of gas giants and their moons. The Galileo mission discovered a massive liquid water ocean hidden underneath a thick ice crust on Jupiter's moon Europa. At Saturn, the Cassini-Huygens mission deployed a probe directly into the atmosphere of Titan, discovering surface lakes made of liquid hydrocarbons. Cassini also observed plumes of water vapor and ice geysers erupting from the moon Enceladus, confirming another subsurface ocean in the Saturnian system. These findings shifted the search for life away from rocky planets toward these active, icy moons. We eventually pushed past the giants into the Kuiper Belt, the field of icy debris at the edge of the solar system. New Horizons reached Pluto and discovered dynamic, icy activity across its surface, revealing an evolving world rather than a stagnant rock. Even at the darkest, coldest edges of our star's reach, our proxies find complex, active worlds. Our robots replace the historical image of a dead vacuum with a new reality, a dynamic and chemically rich cosmic neighborhood. This map visualizes a shift in our understanding of habitability. It shows that the sun isn't the only thermal engine in the system. Gravitational friction can also create zones capable of supporting liquid water. This expanded definition greatly increases the total potential volume for life-supporting environments, revealing that these moons hold more liquid water than all of Earth's oceans. Robotic exploration rewrote the fundamental rules of where life can exist in our solar system. The robotic vanguard continues to accelerate as an ongoing campaign of discovery. Upcoming missions like the Europa Clipper will soon return to Jupiter to probe for the exact chemical markers of habitability in its icy ocean. At the same time, the Dragonfly mission is preparing to deploy a rotorcraft into the thick skies of Titan to study its organic-rich environment. These mechanical emissaries remain our trailblazers, charting the abyss and gathering data until humanity is ready to follow in their tracks.